Alright, so today in class we talked about an introduction to projectile motion. You learned from your experiment that the rate at which all objects free fall on planet Earth is independent of their mass. In the absence of any significant air resistance, and all objects fall at the same rate, which you experimentally determined was about 10 meters per second squared. Specifically 9.81, but we're fine with rounding that to 10 meters per second squared. We give that the symbol lowercase g, and that is one of the notations that means is that it's the rate that things accelerate near the surface of planet Earth when they're free falling. The other significance and meaning that we'll give to that symbol we'll discuss in a couple of weeks. And so today we started applying some vertical launch problems in projectile motion, and we look at something like this where you got this person standing at the height of a 9 meter cliff, and they're going to drop a ball from rest, and the question is, how long will it take for the ball to hit the ground? And so first thing we need to do is we need to identify our given information, which is that since it's free falling, the acceleration rate will be 10 meters per second squared. We know that it's going to change position 9 meters, and notice to the left there I've indicated the positive direction, and I've chosen down, which I'll get to in a minute, and then the initial velocity is 0. And so we look and see if we have any equations that match those given in unknown quantities, and of course our friend delta x equals initial velocity times time plus 1/2 the acceleration times time squared fits. And we can then algebraically rearrange that. The first term goes away because of the 0 initial velocity, and we substitute and rearrange, and we get that, which the square root of 1.8 is about 1.34 seconds. And so it's going to take that ball about 1.34 seconds to fall the 9 meters. So let's look at another example. Let's say that we drop an object from rest, and we want to know how far it's going to fall in the first 3 seconds. Well, once again, we know that the acceleration is going to be 10 meters per second squared, and we know that it's going to fall for 3 seconds, and so we can use delta x equals initial velocity times time plus 1/2 at squared. And notice here I've substituted, or I've written out delta x equals 1/2 at squared and crossed it out. The mistake that students often make is they jump straight to that step, and what I want you to do is I want you to explicitly show that that's only the case because the initial velocity is 0. We're going to have lots of situations here you're about to see where the initial velocity isn't 0, and if you jump straight to 1/2 at squared, you'll, number one, you'll miss the problem, but number two, more importantly, you're saying that something is the case when it's not actually the case. So, but because the initial velocity is 0, it does reduce to 1/2 at squared in this case. We substitute those given quantities, and we find that it's going to fall 45 meters in 3 seconds. Alright, so here's another one. In this case, we're going to actually toss the ball upward with an initial velocity of 5 meters per second from the top of a 5-meter cliff. And now I'm going to get back to that thing that I said I would talk about in a minute, and that is the positive direction. We always need to specify which direction is positive so that we can be consistent with all of our quantities and make sure that it leads us to the right answer. And I gave the students what I call rule number 1, and it's extremely important that you note this. Rule number 1 states that if there's an acceleration, we want to make it along an axis and positive if possible. If there is an acceleration, we want to make it along an axis. You're going to see soon enough that we're going to be moving in 2 dimensions, and we have an XY axis coordinate system. And we want the acceleration to be pointing along one of those axes. And then if we know the direction of the acceleration, we want to make that the positive direction, if at all possible. Now, I don't have to follow rule 1. I can pick any direction as x and y, and any direction is positive, but you're going to just avoid a lot of careless mistakes if you stick to that convention and follow rule 1. So in this case, the acceleration, of course, is going to be down because it's falling. Even though it leaves my hand moving up, it's going to immediately start slowing down, and that's a downward acceleration. So I'm going to choose down as my positive direction, following rule 1. And then that means, as far as my given quantities go, the displacement is going to start at the top of the cliff and end at the base of the cliff, and so it's going to move in the downward direction, so that means it's a displacement of positive 5 meters, but the initial velocity is in the upward direction, and so it's going to be negative 5 meters per second. And then the acceleration, of course, is down, positive 10, and so I substitute those quantities, and I get this quadratic equation. And then you're going to want to familiarize yourself on how to solve a quadratic equation in your calculator quickly, and then you can get the time from that. Now, another question would be if I tossed a ball upward at 12 meters per second and then caught it at the same height, how long would that take? And again, we need to designate the positive direction. I'm going to choose down because that's the direction of the acceleration. And then think about what's going to be the total displacement. Well, I'm going to catch the ball at the same height that I tossed it, and so the total displacement is going to be 0. The initial velocity then is negative 12 meters per second because it's up, and I've chosen down as positive, and the acceleration is 10 meters per second squared. And so then I, again, plug that into my kinematics equation for constant acceleration. Delta x becomes 0. I substitute for the other quantities, and with a little algebra magic, I get to this quantity, which is 24 divided by 10, or 2.4 seconds. Now, this isn't the only approach I could use to solve this problem. We have another kinematics equation for constant acceleration that we could have plugged into. If we just think about the symmetry of the problem, if I toss it up at 12 meters per second, it's going to take just as long to slow down on the way up as it is to speed up on the way down, and so when I catch it, it's going to be going 12 meters per second downward. And so the initial velocity is negative 12 meters per second, and the final velocity would be positive 12 meters per second. While substituting in those quantities to our other kinematics equation, which is that the velocity is the initial velocity plus the acceleration times time, and then algebraically rearranging it and solving for t, you see I get the same answer. I still get 2.4 seconds. And of course that's exactly how it should be. But there's two different approaches there. Just whichever one you feel more comfortable with, you can work. All right, so then in this final example, I'm going to toss a ball up onto the roof. And the roof is 6 meters high, and I'm going to toss it with an initial velocity of 20 meters per second. And I'm going to throw it, just kind of slightly, not quite straight up, so that it does land on top of the roof. And the question is, at what point and at what time will it land on the top of the roof? Again, I need to define the positive direction, and following rule 1, I'm going to choose an acceleration, or a direction to make my acceleration positive. So I'm going to say down is positive, even though 2 of my quantities are up. And when I do that, and substitute into that kinematics equation, I have a delta x of negative 6, an initial velocity of negative 20, an acceleration of 10. And then again, rearranging that and doing algebra, solving for the kinematics, or excuse me, for the quadratic equation, I get 2 roots. I get this 0.32 and this 3.6. Now, let's pause and think about what that means. We always want to make sure we understand what the math means whenever we are trying to apply it. These are times, right? We solved for t, and they're times when the delta x was negative 6. Well, at what time, or times, is the ball at the position negative 6? In other words, the height of the roof. Well, as you can see how I threw it, it's going to happen twice. It's going to happen once on the way up, and then when it comes back down, it's going to land at the height of the roof. And so the 0.32 seconds is how long it takes for the ball to reach the height of the roof going up, and the 3.6 seconds is how long it's going to take to go all the way up, reach its maximum height, and then come down to the height of the roof. And so you've got to think about, which of these roots are important to you whenever you have a quadratic equation. In this case, I use the example in class of if I was tossing a ball upward and hit the ceiling, then the kinematics, or excuse me, the quadratic equation would give me the root of when it was at the ceiling height going up, but then also if it had busted through the ceiling and then come back down, there'd be a second time. And in that case, I'd want the first time, the first root. Or in this case, I wanted the second root. Or I use the example of I like to ask questions like if your friend is standing on top of the roof and they're not going to see the ball until it hits eye level at the roof height, how long will they have to adjust and run and catch it? Well, of course, they won't see it until the first time, the 0.32, that's the time that it's at the roof height, and then they have the difference between the 3.6 and the 0.32 in which to adjust and move over and catch the ball. So that's an introduction to what we would call vertical launch projectile motion. And next time in class we're going to add a dimension and do horizontal launches as well.